Thanks everyone for joining us this morning, and thanks for responding to that poll. Obviously an interesting response. Good to see lots of AWS users here, SageMaker, step functions, interesting number of internal tools, and a big spread across the others. So hopefully you'll all enjoy what we had to present this morning. But yeah, very interesting to see those results. So we might just get started. My name's Nick. I'm the CEO and co-founder of Kelsen. Joining me today is Alex and Matt. I'll just let Alex introduce himself.
Hey everybody, my name is Alex Chung. Before we dive too deep into this presentation, on behalf of Amazon and AWS, we hope that you are safe and well. Regardless of where you are in the world, this is truly unprecedented times. And we hope that you're first and foremost taking care of your safety, your health, and those of the others around you. And if there's any way that either the Kelsen team or at Amazon and AWS can help in terms of your organization's response to these global challenges, please do reach out if we can help in any way. Besides that, my name is Alex Chung. I am one of the product managers on the SageMaker Machine Learning platform. And specifically, I handle our integrations between our ML systems and open source tools such as Kubernetes and Kubeflow.
I'm Matt Rose, I'm a machine learning engineer here at Kelsen. I've been here for about 2 years now. My position pretty much involves developing end-to-end machine learning pipelines, all the way from data collection, annotation, modeling, model evaluation, and serving.
So as I mentioned, I'm Nick. I'm the CEO and co-founder of Kelsen. Kelsen is a Brisbane-based machine learning and deep learning organization. We have about 38 people in our team here, which spreads the full stack from data scientists and machine learning engineers through to back-end software developers, cloud engineering, even mobile development, front-end engineering, product management, business analysis, and so on. We have clients across the world, including US, in Singapore, Thailand, New Zealand, and the UK. We actually split our business up into 3 key areas, and this is just a very quick introduction to us. We have a research team, and our research team focuses a lot on problems in healthcare and life sciences, but does do a lot of work in AI safety, specifically Bayesian methods and quantifying uncertainty in deep learning systems. We then look at our professional services organization actually as a product studio, and we focus as an organization on building production grade and in production machine learning systems. And that's why we have a full stack engineering capability, because we think that the most value that can be generated from machine learning systems is when they're a product and they're deployed in the world in a production environment. And so that's really what we focus on here and what our team does day to day. We also have a MLOps capability, which has been an internally focused team for the last couple of years, but is increasingly working directly with our partners and customers to help them deploy their models and to manage their models in production. We're fortunate enough to have a round-the-clock support desk and an SRE team focused on our models, and so we're slowly extending that to some of our customers to assist where they don't have the scale to do so. So we focus on a number of industries. Healthcare and life sciences and financial services and insurance are the spaces that we do most of our work. And what's important to note about those is that they're regulated industries. And so often we're finding ourselves operating under regulated environments, whether that be in healthcare, which we're going to talk about today, or in APRA regulated systems for credit management, et cetera, in financial services. It's important to understand what the regulatory environment is that you're operating in and how your MLOps can support compliance. We also work in resources, mining, oil and gas, retail, food and travel, and public sector. So we have a really broad set of experiences working with customers deploying machine learning systems. This is what we call our virtuous cycle or flywheel for those familiar with the Amazon terminology. We do see this play out a lot in our customers, and it's why we think that production use cases really matter. What we find is that our customers who invest in early use cases and start generating business value from those use cases generally invest a lot more and build a lot more machine learning systems. So what we find is it's much more likely that our customers will have many machine learning systems than one. And those that start with one will grow to many quite quickly because they actually see the value, and the value drives more investment, more use cases, more data, more modeling, and so on. So MLOps, it is definitely, I think, the most overused term, at least in the last 3 months, but it is a rapidly emerging field. I would say that the way that I look at the term MLOps is it's an umbrella term to capture a number of challenges that data science or machine learning teams encounter when trying to manage the full life cycle of models and deploy them to production. And so in many ways, there are a number of solutions that are necessary to achieve a mature MLOps standing. We're going to talk about some of them today. It is a very broad umbrella. This is, and in many ways, this is an opinionated presentation. This is how we see the world and the solutions that we've come to the challenges that we'll raise. But like everything, it's not a textbook, and that different solutions are going to fit into different customer settings. We're still on the journey at Max Kelsen. We've been doing machine learning in production for a long time now, but we are definitely improving every day and strive to improve every day. These processes aren't adopted by teams overnight, so there is a commitment that you need to make to really ensure that you do see the benefits of having a mature MLOps stance. It's not just turn it on and it'll happen. I think and I wanted to open with this observation, one of the things that we've found over the last couple of years of focusing on this area is that software engineering actually holds many lessons for data science and machine learning. Software engineering teams have been putting code into production in mission critical environments for a long time. They've built a lot of tools and a lot of processes to make this work. And at its core, machine learning and data science is software engineering. And so in many ways, there are a lot of lessons for us to learn from the other side of the fence, and we should heed these lessons. And I think just finally, we're going to talk about two tools that go a long way to making it much easier to operate machine learning systems. But there isn't a silver bullet. There's not, as I said before, a switch that you can just turn on and all of a sudden, your MLOps is resolved. But the two tools that we're going to talk about today do make your life a lot easier and go a very long way to resolving a lot of these challenges. So this is a slide. This is a tweet that is quite old now and is very overused, even in my slideshows, but in many people's slideshows. But I think it does really well capture some of the challenges that we have and the reason why the MLOps topic has become so big over the last year or two. And that's it. For this person, it took them 3 weeks to develop a model, and then it was over 11 months and the model hadn't been put into production. Now, I would say this is what life was like for us a number of years ago. These days, the time to production is much shorter, and we've achieved very, very short times to production. And some of the ways that we've done that we'll talk about today. But I want to start with some of the challenges. We're going to talk, or at least Matt and I are going to talk in the context of a customer use case. I think it's a really good customer use case, A, because Matt's been working on it for the last couple of months, but B, because it does represent a machine learning system deployed in a safety critical system. So we're working with a customer, a global healthcare customer, to develop a medical device. That medical device is a class 2A, class 2B, depending on how you cut it, medical device, meaning it's a diagnostic, and it will be regulated by the FDA and the TGA as it comes to market. It's based on computer vision, so it's a deep learning based system. It has clinician in the loop processes to ensure that inferences that are questionable are escalated to clinicians. The models need to be retrained regularly, and their promotion strategies need to be governed by an algorithm change process, which is what the FDA are now requiring any medical devices which have continuous learning systems comply with. And the MLOps stance that we'll discuss today really assists you implement an algorithm change protocol. It's a project that has multiple machine learning engineers and multiple application engineering engineers working side by side, iteratively and rapidly to develop it. So it's not a single data scientist, working on a model for weeks on end. And we had to acquire and label the data set as well as part of this project. So it is a very broad project for us to discuss with a range of challenges, which I think are very topical to what we're talking about today. So I get the easy part of today. I get to talk about the challenges, and then Alex and Matt get to talk about how we resolve those. There's a very long list of challenges of doing machine learning in production, and those challenges get longer the more specialized or the more high risk the environment you're operating in is. These are some of the core challenges that I see. I see challenges around overdependence on the person that developed the model. So, the single data scientist, the undocumented, untested notebook that trains a model that no one understands, and that data scientist may leave the organization or be focused on other things when it comes time to update that model or to make a change to that model. that actually feeds into the challenges of reproducibility. Reproducibility is a very broad topic. It starts with, managing your Python development environment effectively, so that you don't have packages break and dependency nightmares when you do revisit that notebook, all the way through to, ensuring that hyperparameter sweeps and settings are reproducible time and time again. And obviously we've seen that it's a big challenge in academia. Explainability and bias is a topic that is talked about a lot in the terms of AI safety and AI ethics. We actually see it as being a core part of MLOps. MLOps is about managing your models, managing the risk around those models, both from a deployment point of view, but also from a procedural point of view. And so any explainability or bias detection and correction that's required, either at the training or inference step, needs to be managed as within your overall MLOps workflow. We think a lot about, obviously, concept drift. That's why we advocate building automated retraining pipelines for any model that lives in production. The fact of the matter is that data does drift. It's just a question of how quickly and how catastrophic that drift is. I'll give an example. We have a customer that makes millions of decisions a week based on models that we provide for them, and those models drift a number of % a month. So if you don't retrain that model and you let it sit there, then that has a fairly significant financial impact on that customer as the drift is incurred and the models become stale. Understanding the cadence of the drift or the nature of the drift is really important so that you can set your retraining at the right cadence. Cost is also really important. Alex is going to talk a bit about the innovations that Amazon's bringing in market to bring inference costs down. These are really important. I have seen, and I'm sure everyone has seen, inference costs that have undermined the ROI almost entirely of models that have been developed. So understanding your inference architecture and ensuring that you're doing it in a cost-effective way is really important. The same goes for training, right? We shouldn't have notebooks backed by 8 V100s while we're working in pandas. It's just that simple. But those things still go on. But a couple of other notes. Changes in upstream data, so data testing is important, and that long time to production problem. But as I mentioned, this is just a snapshot of a couple of challenges. There are many, and they change across projects and across customers. So this is what we see, or what we would call MLOps 1.0. It looks a lot like our lives, 2-3 years ago here at Max Kelsen, and I'm sure it looks a lot like the data science experience in many of the people on the call and many of your peers. It's a notebook-driven experience. That notebook is run on a local machine, on an AWS EC2 instance, probably using the deep learning AMI, or preferably, it's migrated to the Amazon SageMaker notebook experience. But it is all notebook-driven, probably training in offline data, and the model is outputted as an artifact, which is then handed over to the ops team to be hosted. This has a number of pitfalls in our view. Firstly, that the notebook development is really good for experimentation, but not good for a manageable, deployable system. And it may be for 1 or 2 models in production, but when you're at 10 or 50 or hundreds, as we've seen, this is simply not scalable. It's too brittle. In development, it's not collaborative insofar as it's very difficult for multiple engineers to be working in parallel simultaneously on a single machine learning system. It's much more directed to individual work. And code and data testing is very difficult. So unit testing or data testing, as I discussed before, to detect for upstream data changes is very hard in the notebook setting. It's much easier in a workflow setting like we'll discuss. The offline data leads to the training inference skew, which is well known and well talked about. I've certainly seen it multiple times over the last couple of years here, where the training data is just not representative of what can be achieved in real time at the decision point. And so understanding what your actual live data looks like and developing models for that and not for the training data is crucial. In this setting, ops have a very narrow view of the world. They understand the model artifact and the serving infrastructure around it, but they don't understand what that model's doing or the broader machine learning system that produced that model. And so it makes it very hard for them to monitor, manage, and debug issues in production. The retraining process might be scheduled, it might be manual. The release process normally isn't governed by CI/CD. It's I've put the new model in the bucket, team in ops, can you please promote it? And then obviously we have challenges around inflexible training hardware insofar as the training hardware is limited to what the pipeline is backed by.
I just want to take a moment. If you just go back one slide to that MLOps graph, this really represents what we see with many customers around the world. It almost, irrespective of the company's maturity, to some extent, this MLOps quote-unquote 1.0 is still around with either experimentation or in some cases where models that have been created and then the architecture has been built around it. Nobody really wants to change it because it kind of works as long as you aren't doing regular updates. And I can give you, just quotes from this probably about 6 years ago when I was running my, before I joined AWS and many other companies before, I ran a quantitative hedge fund. And this was the exact process that we had. So this more or less has been the kind of de facto standard. But with AWS, we've really built a lot of offerings so that you really can standardize this. And you can also take it to the next level in terms of adding in many of those bells and whistles that can correct for issues like model drift and the other challenges around GitOps and really making sure that you have consistency across the board. So if we can go back to my first slide, that's +2 from where we are right now. Perfect, thank you. From AWS's perspective, we really offer 3 classes of products to service the machine learning stack. And at the very bottom are what we call frameworks and hardware infrastructure. So we offer TensorFlow, PyTorch, and MXNet. With TensorFlow and PyTorch, we actually offer modifications on top of what open source already has. So for instance, we put in something called an S3 plugin that actually reduces the latency time for TensorFlow and PyTorch to access S3 buckets so that you are able to reduce the load time on data into the TensorFlow models and also the PyTorch training tensors as they're created. We also offer things like deep learning containers and deep learning omnis, which offer our bundled frameworks on top of an easy to load image that can go on EC2 or EKS or SageMaker. And then we also have very specific hardware. So elastic inference allows you to take advantage of fractional GPU instances. So this has already been available for a year. This is a feature that is also coming out for the A100s for NVIDIA, but we've already had this out. And this allows customers to use CPU instance types and also get fractional amounts of GPU for cost efficiency. We also have tools like Inferentia, which is our custom ASICs, which means ultimately if you're doing inference on the cloud and you want some degree of GPU level performance, but you don't want the price for specific models, you can actually leverage Inferentia, and which can drive down your cost because it's all proprietary hardware on AWS. In the middle bucket, we have what's called the SageMaker ecosystem. So SageMaker is really our managed service layer. It spans tools like the SageMaker Studio, which is a Jupyter environment with many other bells and whistles. You also have ground truth labeling that the Max Kelsen team alluded to, and we'll talk about a little bit further. And you also have tools like SageMaker Neo, which essentially is model inference acceleration. It takes the same model tensor, and then it optimizes it using SageMaker Neo, which under the hood is a managed version of TVM, an open source library. And then it packages it so that it can run in an optimized manner for target hardware, whether they be IoT devices, on-premise cloud solutions, or others. And at the very top is what we call AI services. These build on top of our SageMaker platform, but for you as a customer, you basically see an API endpoint. It allows you to do things like image recognition, text recognition, PDF reading, and many other common use cases of machine learning. And in terms of what the model lifecycle machine learning workflow process looks like, we really see this more or less in 4 stages. You probably understand most of this intuitively. First, it's collecting and preparing training data. So this could be tabular data. This could be amorphous, computer vision, NLP, corpus data. And this could also just be anything else that's in your data warehouse. You have to collect it, you have to sanitize it, and then you have to prepare it for the proper format going into your model training inputs. Next up is the model algorithm itself. So note, this is different from the model artifacts, what gets deployed. This is the model algorithm. It's how you design the tensor if you're using a deep learning neural network, or it's what type of algorithm you're using. If you're using classical machine learning, on SageMaker, we actually bring algorithms like ResNet, K-nearest neighbor, and other common algos as built-in solutions that you can leverage, or you can take advantage of things like Detectron 2 from PyTorch with SageMaker. On the bottom right, you basically have the training process and the workflow that you have as you're feeding models in to identify your most optimal artifact. So this could be things like hyperparameter tuning tools that are offered by SageMaker, experimentation management, artifact lineage tracking, and then also the ability to debug, which means essentially inspecting the model tensor states as your model is training so that you can actually understand whether or not your model is going to converge early on, which ultimately can save you a lot in terms of your training bills later on if you're doing more intensive GPU-based training jobs. And then finally, on the bottom left, this really is that deployment into production, which is a combination of model monitoring, ensuring that you have scaled compute, auto-scaling, and the notion of being able to redeploy models in an A/B, ongoing basis into your environment. So let me just go to the next slide. Essentially, this just gives a little bit more description into it, but amongst all these different pieces, SageMaker is designed to be the one-stop shop where you can take advantage of all of these different needs from an environment where you would have minimal DevOps. You have the luxury and flexibility of a fully managed service while also taking advantage of open source conventions with the SageMaker offerings that we'll talk about in the next couple slides. So ultimately, what we've seen customers want is a unified experience for development. And within this, we have a tool called SageMaker Studio. If you're familiar with Jupyter Lab, there's Jupyter Hub as well. SageMaker Studio looks and feels a lot like Jupyter Hub, but it's wholly integrated with the remainder of the SageMaker ecosystem, taking advantage of experiments, debugger, other things like model tracking, artifact stores. So you can get a one-stop view with all of your different models, collaboration of your notebooks, and also the GUI so that you can easily deploy and view all training jobs and deployed models from one location. So this ultimately becomes a way where you have an IDE for all steps in your model development process. And we're proud to say that we're the first machine learning IDE in the industry today. And we are just continuing to invest in this process across the board. And ultimately, this feeds into another portion of our conversation today, which is open source. We hear a lot of customers asking for tools like Kubernetes and Kubeflow as part of their machine learning process. And ultimately, this is because many customers want to have the flexibility of open source standards and conventions. Whether or not you have engineers that are trained in-house or brought on from another company, whether they be developer contractors or new hires from other firms, Kubeflow and Kubernetes are standards that are almost universal regardless of where you go, whether they're educational institutions or in private enterprises. And within this Kubernetes Kubeflow stack, they jive well with the notion of being on cloud or on premise. And this gives you a unique trifecta where you can have ultimate flexibility of your ML stack. And when you tie it in with SageMaker, you basically can get all the advantage of, once again, that managed service, training, tuning, serving, scalability, while also remaining within this open source convention world. And probably the most popular tool that we've seen this year is Kubeflow pipelines. Kubeflow ultimately is a series of different packages, and specifically pipelines itself is the most popular of them. It offers workflow orchestration. So when you think of creating one of these pipeline jobs, it could be something like take data from data source A, convert it into a CSV or Parquet format, feed that into a training job, run that against an existing data set that we use for baselining model performance. And then after that, if it's better, promote it into production. So this end-to-end can be encapsulated into a pipeline. And essentially, Kubeflow is one of the open source tools for running this with a slick GUI. And this also provides tools where you can, in an experimentation format, so well before you're ready for production, track all of your different runs, see how they compare against different similar runs with either different data, different hyperparameters, and then ultimately understand what needs to be changed for your ultimate model artifact. And then finally, it's almost as simple as changing a Git command, and you can feed that into your GitOps process and you promote it into production. Kubeflow really offers a lot of different flexibility, and we're really proud to have support of Kubeflow in terms of integrations with SageMaker. And ultimately, we've invested in these integrations because we hear customers across the board asking for help in terms of provisioning these type of environments. Scaling machine learning is hard. Kubernetes requires a dedicated DevOps team. And on top of that, Kubeflow itself introduces more complexity on top of Kubernetes, because now you have to think of things like taints and tolerance, which simply means GPU jobs need to run on GPUs, CPU jobs have to run exclusively on CPUs. And if you mix those two interchangeably, you actually get an environment where you might be billed for a GPU instance when you completely did not need it for your environment. And also ensuring that you have regular availability, distributed training, spot training as simple one-click solutions are not possible unless you invest in having a sophisticated DevOps team constantly maintaining the system and also setting up new environments as you expand to different regions, such as different availability zones or different regions around the world. And ultimately with SageMaker, you get a managed versions of all the different packages within Kubeflow. So Jupyter Notebooks, we have SageMaker Studio. For all the TensorFlow, Spark, and data preparation tools, we also offer variants of that within SageMaker as a managed container. TensorFlow, PyTorch, MXNet, we offer the AWS modified versions. Model tracking, model deployment, hyperparameter tuning. Once again, we offer very similar tools that actually are encapsulated with our infrastructure so that you can easily scale them across all of your different use cases, different models, and also around the world with literally, once again, it's as simple as a click of a button. And if you think about how this ultimately blends together, SageMaker offers that managed infrastructure, spot training, ground truth data labeling, hyperparameter tuning, model monitoring, scalability, built-in algorithms. So really all the benefits of the common tools that you might need, with also the benefits of open source, which is, once again, the idea that you have universal constructs that hopefully most of your engineers will intuitively understand because they are either familiar with Kubernetes or Kubeflow. This also integrates very conveniently with your CI/CD system in a way that is, if you're already standardized on Kubernetes, you can take advantage of accelerated machine learning by blending our products together. And ultimately, this is convenient for repeatability. And we offer two specific products that allow customers to blend open source with SageMaker. And the first, and probably the most popular in terms of number of customers, is our SageMaker component for Kubeflow pipelines. If you're familiar with Kubeflow, you know that you ultimately are building what are called components. And these components are set logic that run specific steps within your pipeline. And we offer the SageMaker version that you can build on top of, or you can use directly to compose your pipeline. For another set of customers, those that I would consider more advanced and have their own workflow orchestration solutions, so their own custom Kubeflow pipelines internally, they can use our SageMaker operators. And these are used by a myriad of different customers from different industries. And this allows the customer to basically create their own abstraction on top of our operators, but basically be able to submit jobs into the control plane of Kubernetes, which then, instead of running locally on Kubernetes, will be submitted into SageMaker for execution. So once again, for both of these products, you have the open source conventions. From the SageMaker components, it's Python native. If you have your own DIY Kubeflow install, you can take advantage of SageMaker from within the Kubeflow pipelines dashboard. You construct it using the Kubeflow DSL, and this will all run on SageMaker. And you can mix and match between your own build components and SageMaker components interchangeably. On the right-hand side, you can see SageMaker operators, which you're submitting what are called custom resource definitions. Those are the universal constructs of a Kubernetes control plane job. And this will run on top of any of your existing abstraction on top of Kubernetes, whether that be something like a GitOps process using operator submission, or if you're a company like Lyft, who did a reInvent session with us last year, you have your own workflow orchestration tool called Flight. Intuit uses a tool called Argo, and all of this ends up being a very similar interface end to end. Once again, this is more for advanced customers. And when you use a SageMaker ecosystem and you combine that with open source conventions, AWS is your one-stop shop where you can have almost everything that you need to have a wholly integrated ecosystem. We talked a little bit about SageMaker. There's a lot more features and products that we can dive into as well. And if your enterprise or organization is interested, please do reach out to us at the end of this webinar. But we also offer tools like ECS and EKS. EKS is a managed Kubernetes control plane interface where you can also easily attach additional nodes subject to what your environment requires, GPUs, CPUs, but you still have a lot of under the hood configuration that you have to do and customize to your specific environment. We also have open source contributions into Kubeflow that makes running Kubeflow on AWS really easy to do. And then on the right-hand side, we have an image registry. It's very similar to Artifactory, if you're familiar with that, or Docker Hub. We offer our own managed version of container solutions where you can track all your different repos for pre-built images that then get deployed either in production for training or for experimentation. And then finally, this mixes together with all the different hardware that we discussed earlier on. And in summary, I just want to iterate, Kubernetes is hard, but Kubernetes is also the way that most companies want to build their machine learning workflows and environments for production. With SageMaker, you really get the blend of both worlds where you can have tools like managed notebooks, managed studio environments, managed compute, but you can have the open source conventions that your developers are likely very familiar with, or that your enterprise has chosen to take for strategic purposes. And this allows you to ultimately have the blend of both worlds where you can have a multi-platform, multi-cloud strategy on-premise, on cloud, while still having the benefits of reduced DevOps expense, which ultimately comes down to a TCO conversation, total cost of ownership. Everyone wants to have the sexiest, the most sophisticated machine learning products, but everyone also wants to nickel and dime and have the most cost-effective ROI that they can get. Using SageMaker components, using SageMaker operators really allows you to have both of those put together. And I'm going to give this back over to Matt at the Max Kelsen team, where they'll actually walk you through an end-to-end of how they envision building this out for customers and what we've seen here at AWS as well.
Sweet. Thanks, Alex. So yeah, as Nick mentioned before, the vast majority of my time for the past couple of months has been working on that computer vision based medical device. And right from the start, we wanted to go in with a game plan. And we said, we want to build this with the Kubeflow stack on an AWS EKS cluster, and then utilize SageMaker for the ML services whenever we could. So hopefully I'm going to share some of the tangible benefits that I personally noticed as a developer using these, and then some of the tangible benefits that we noticed as a team in the kind of development speed and efficiency of this. So this is a pretty big upgrade from the MLOps 1.0 diagram that Nick showed. There is a lot of extra infrastructure here, so I think we're going to put up a little poll now just to see basically if you're the one managing your own infrastructure or if you've got support, because I know that I'm really lucky here at Max Kelsen to have a team behind me, the cloud team and the DevOps team, to basically put all that stuff into our AWS accounts when I need it and when I want it, pretty much. You can see the results there. I guess it's a pretty even split. The ones who said yes, you're pretty lucky. So yeah, this diagram is basically what our general infrastructure looks like in this medical device without a bunch, or actually without quite a lot of the bells and whistles that come with a highly regulated environment, all around the auditability and tracking and things. You can see right at the start, we still start with notebooks just for data exploration and analysis, because they are good at what they do. They're a great visualization tool, especially for something like computer vision, where you essentially just want to be looking at your images before you feed them through your pipeline. Then we move into our orchestrated experiment workflow based on Kubeflow pipeline. You can see all the steps there that basically represent those components that Alex was talking about, with our training components backed by AWS SageMaker training jobs. And so you can add any custom components in here you want with any logic that you can conceivably think of, as long as you build it in the way that's kind of described by Kubeflow. And so after this pipeline, we can iterate quickly, we can generate models, and we can analyze those models in a sort of development flow. After we've kind of settled on what pipeline we want to use, we commit that to a version control system, which then builds, packages, and tests all our containers underlying those components. Now, this continuous integration also allows continuous deployment of the pipeline itself, considering it like an entity in your machine learning system. This pipeline can be run with automated training jobs or retraining jobs, scheduled whenever you want, however frequently you want, and they generate the new trained models, which are then stored in S3. So the model serving step kind of encapsulates any other custom logic that you want to implement before you promote models. So it could be manual intervention, or it could be just automatic checks. And then it goes through and you have that model performance and monitoring offered by any of the hosted inference endpoints from SageMaker. So right at the start, these pipelines are built by, or basically made up of those modular components. And it's a lot easier to productionize models if you build with that thought, or with that thought in mind right at the start, instead of kind of tacking on, oh, I want to promote this model production as a kind of afterthought. So we started with the mindset in this project of developing modular components, basically containers that fulfill one purpose and one purpose only for the, I guess, for the use case of chaining together to make that full machine learning workflow. So this kind of mindset offers a lot of advantages. Some of them are more individual as a developer, and some of them are like team-based. Some of the ones that I found more individual-based is just trying to remove that annoyance of recreating your notebook environment. Maybe there was some like exorbitant sequence of steps that you had to take to install some package, and even a day later, it's pretty hard to remember exactly what you did, and you don't want to spend hours again trying to install this one library that you want to use. So if you define this kind of recipe of your environment in a Docker file, it allows you to reproduce it time and time again, basically on any machine, unless you're running Windows and trying to run Linux containers, but that's a little side note. Another thing that I found really good is it allows you to basically test your code very consistently. If you run the same tests on the same container, it's going to spit out the same output. So you can pinpoint breakages basically when you make the code change that causes that breakage, and there's no delays like days or weeks after for that feedback to come back to you. Some of the team-based ones is what Alex touched on already, is those components are very easily shareable. They're just defined as YAML files, and so the SageMaker ones are sitting in the Kubeflow pipelines repository. They're very easy to just essentially clone down and put in your pipeline with basically one Python function call. As Nick touched on as well, this promotes collaboration and like efficient teamwork, because you can define your inputs and outputs of any components in your pipeline, basically fan them out to a bunch of different engineers as we have, build them all in parallel, come back together, and there's no nasty surprises when you're trying to glue them together. So the CI process with these container images that underpin your components is we do it when we push code changes to our Git repository. Our CI tools like AWS Code Build can build and test those containers and then basically notify you if anything breaks. So one small trick we found with machine learning training code specifically is that you can run a smoke, or what we call a smoke test, basically feed in 5 or 10 data samples of dummy data, train for one epoch, and just make sure your whole loop runs end to end. Because we have been bitten, and me personally a couple of times, of training models for hours or days and then there's a typo in my save location, so the whole thing crashes and you kind of just wasted a whole bunch of your own time and a whole bunch of money. So one way to also speed up this kind of development loop if you're using Docker images is to take advantage of the caching mechanism. So if you start from the top of your Docker file with the thing that's least likely to change, so you might use a base image like the SageMaker deep learning containers that already have machine learning libraries and like GPU drivers, etc. installed. Then you move on to, we use some of the custom C libraries that computer vision things require, then our Python dependencies after that, and then finally our actual application or component code. Because this is the thing that's going to be changing the most, it allows us to basically not have to reinstall all of those dependencies time and time again. You just build and pretty much instantaneously you have a new container with your new code. Now, once you've got all these components built, you can chuck them in the pipeline. So this is a simplified version of our retraining pipeline currently. And you can see at the start, we've got a bit of a fan out component, which kind of architects the rest of our workflow. This spans out into currently five parallel SageMaker training jobs, utilizing that SageMaker component. Now we use this component with a custom Docker image, and so this takes advantage of the on-demand automatic scalability of the compute, as well as managed data ingress and then model egress to S3. Now, this is there's only a couple of code changes that you need to make if you've already got your Docker image built and are running it as a component. There's only, like I said, only a couple of changes you need to basically put it into SageMaker and allow it to do what it does best. This removes a bunch of annoying resourcing errors, like one that we've run into is a cluster autoscaler killing instances in the middle of a retraining run, which is, again, very annoying. And then you can see we've just got some basic gating logic, so a metric comparison, just checking that the one that was trained is better than all the previously trained ones. And you can add in any other components in this kind of layer as you want. So as Nick mentioned, problems like explainability and bias detection and data drift, you can just add components in here that check those things based on your trained models. And then if they fail, you don't promote. And if they pass, you can promote. So any relevant, like I said, any relevant logic can be really quickly added to these components because they are just single Docker containers with single purposes. So if we want regular retrains, we could add some logic in the fan out component that basically says, oh, look at this database. If we've got 300 new data samples, kick off a retraining run. If not, wait till tomorrow. And so with these pipelines, you can develop very quickly as well, because you can essentially compile them, upload them to your cluster, and submit runs with a couple of lines of the Kubeflow Python SDK. This compiled pipeline is defined again as a YAML file, much like their components, and this allows you to also version control and store their definition. So this allows for continuous deployment of your training workflows as an entity, because they can just be applied to whatever cluster that you're working through. We also utilize the AWS ground truth component in this medical device because we did have to collect our own data and we needed to get annotations. So we set up some like sequential labeling jobs with ground truth that had a bit of custom logic in between that allowed us to check on heuristics or extract some information from some of those initially annotated images. Because we also needed expert review on these annotations, we can spin up more pipelines to spin up those review jobs. And so the point is here, the pipelines aren't just for model training. You can essentially use them for any part of the full data lifecycle in your machine learning system, like data transformation or feature engineering or any number of things. So I guess the last step in this kind of full MLOps process is actually making these models available for live service in production. So on the right, you can see model endpoints defined declaratively with basic, if you're familiar with Kubernetes, the Kubernetes like YAML syntax. And so the learning curve to go from any sort of familiarity with Kubernetes to deploying these machine learning models with things like AWS hosted inference endpoints is pretty small. And even if you're not familiar, it's still just a bunch of keys and values that kind of tell you exactly what it's about to do. So defining your model endpoints declaratively like this also allows, again, you to utilize version control as the source of truth for these production models. You can look at a GitHub repo somewhere and it tells you exactly which model is serving when. This sort of, I guess, mindset also allows you, or also helps us solve basically 90% of our healthcare regulation problem, because we know exactly what pipelines produce which models and which models are serving when. So yeah, like Alex mentioned, the last step in our retraining pipeline is actually opening a Git PR with a version change of the model that it's produced. And this kind of signals the handover to our more traditional ops team. And so we can leverage their expertise in managing assets through the dev, pre-prod staging, and then production lifecycle. So with infrastructure like these pipelines, I could probably swap out a new computer vision algorithm if one comes out that I'm interested in, or maybe add in new image augmentations, commit that pipeline to Git, and then with a full few new Git pull requests, we can have models serving in production pretty seamlessly. I guess with this thing, with the end of this serving thing, we're pretty interested in seeing the maturity after you've kind of seen this stack. So yeah, if you can just fill in this poll as well.
Awesome. Thanks, Matt, and thanks, Alex, for your insights in both areas. Obviously, it's been a relatively short time, and this is a huge topic. So I think we've touched on some really interesting areas, but no way exhaustive, across the full ambit of MLOps. So what's the call to action here? Look, as I mentioned before, we're really keen to work with our customers to help them implement some of these platforms, policies or procedures that will help them run a more mature DevOps or MLOps capability. For us, the next steps are working with you to evaluate where you're at and what the key pressure points and pain points are that can be resolved with some of these platform technologies. And then finally, help, engaging us to help build out, develop some best practices and some paved roads within your organization. So we'd love to work with you. We'd love to hear from you. But thank you all again. Hope you have a great day, a great night, depending on where you are.